Inclusion, exclusion, which not only is tons of fun, but it's something quite useful. We will use it to count onto functions for finite sets A and B. You might also see it in probability, where it's another, I would say, big use of inclusion, exclusion in a probability class. Well, let's talk about so far what we can do before we jump into today's lesson. Let's say A and B are finite sets. So we can count first of all the number of relations from A to B. We can count functions from A to B. We can count one-to-one functions from A to B. All of this is in our exam review packet, for example. And then if, let's say, the cardinality of A is strictly less than the cardinality of B, or I could really say less than or equal to, but I will just say less than for the moment, we do know the number of onto functions. This, in fact, let me write from A to B. We have discussed in more than one video, although we proved it in the last one with the pigeonhole principle, if the cardinality of A is strictly less than the cardinality of B, there are 0 onto functions. Okay, well, we would like, and we will today, figure out when the cardinality of A is bigger than or equal to the cardinality of B, the exact number of onto functions. And we will do this through inclusion, exclusion. But before I do, let me give you a reminder about, because we have discussed inclusion, exclusion when we have two sets, certainly. So let's recall, if we have A and B finite sets, again, same setup, finite sets. But in this case, I'm not counting functions, relations, or anything like this. I'm just thinking about cardinality of A, cardinality of B, cardinality of the union. And the picture we associate to this is a Venn diagram like this. Here's A, here's B. And we know that the cardinality of the union, you can't just add the two cardinalities. Well, you can if they're disjoint, but that's not the general case. It's cardinality of A plus cardinality of B minus the cardinality of the intersection. And this we discussed, okay? How do we get this formula? Well, you think about adding, right? You add up all the elements of A, then you add up all the elements of B, and you notice when you do this that everything in the intersection has been counted twice, right? Once when you counted A, once when you counted B. So you must subtract off everything in the intersection one time so that everything in here is counted only once. And this is where this formula comes from. And we use this. For example, well, maybe I'll mention what this is called. This is called the principle of inclusion, exclusion. I'll do an example, and then we will talk about when we have more than two sets, and that's really what's new. The principle of inclusion, exclusion. And this principle for two sets, as I mentioned, this we have done, but let's do an example where we use this in counting. Maybe I will go back to black. Okay, So the example, I'll actually pull one that came off our Exam 2 review packet. So this is one we have actually worked through. Well, let me figure out what it is. It says, how many positive integers less than or equal to 100? How many positive integers less than or equal to 100 are divisible by 3 or 5. Okay, now, well, I have it here, but I will draw a Venn diagram again for this particular problem. We have integers divisible by 3. We have, okay, less than or equal to 100, divisible by 5. So for instance, if I think about my universe out here, U, this U consists of, say, I'll write it in set builder notation. It's all X and Z such that positive integers. Oh, I should say X and N, excuse me. Positive integers such that X is less than or equal to 100. Okay, that's my universe. And then if I wanted to be formal about it, I could call this A and this B, where A is the set that's divisible by 3. B is a set divisible by 5, like this. Okay? And then we want the cardinality. So if A, maybe I'll write it, U is that we have divisible by 3. I'll just write it like this, divisible by 3. B are the ones that are divisible by 5. And then what we want is, it's an OR, so we want this. And so we just count the number of things in A, number of things in B, number of things in the intersection. It's exactly this inclusion exclusion as we saw. Now, here, the number of elements divisible by 3, there's a few ways you can think about it. You could take, let's see what, 100 over 3 and take the floor. I always just think, what's the biggest integer less than or equal to 100 divisible by 3? It's 99. So we'd have 99 over 3, which is 33. This is the cardinality of A. And the integers are 1 times 3, 2 times 3, 3 times 3, out to 33 times 3, like this. And then the biggest integer less than or equal to 100 divisible by 5 is in fact 100. So this is 20. This is the cardinality of B. What's the biggest integer less than or equal to 100 divisible by both? Well, to be divisible by both, so here, A intersect B, this says you're divisible by both, or equivalently, you're divisible by 15. 15 times 3 is 45, another 3 is 90, another 15 is 105, that's too big. So we have 15 times 6 is 90, and that's the biggest one. So we would take 90 over 15, which is 6. This is the cardinality of the intersection. And then we use the formula that was down here, and I erased for the union. This here is, well, it's 33 plus 20 minus 6, 53 minus 6, we have 47, okay? And this is an example, in fact, an example that we have seen, you may or may not remember, but we have seen of using inclusion exclusion for 2 sets, okay? It's a counting tool, right? Now, let us discuss 3 sets, and then we will work with how is this going to get us to counting on 2 functions. So let me discuss the principle of inclusion exclusion for 3 sets, A, B, and C. Or maybe in fact, I will now, instead of saying A, B, and C, I will use indices. So suppose we have 3 sets, A1, A2, A3, and these are finite sets. And I switch to this because we will state it more generally with n sets. So that's why I switched from ABC to A1, A2, A3 like this. Okay, now I can't really draw Venn diagrams past 3 sets, but I can for 3. Would be something like this. This is one that shows every possible overlap. This would be A1, A2, A3, and the number of things in the union. Okay, this is inclusion, exclusion, excuse me. And it's the same idea. It really comes from you include all these and you exclude, that's subtracting, and then you include and then you exclude. You include, you exclude. It's a bunch of adding and subtracting that comes in this formula. So let's see what this is with 3 sets. Well, the first thing I would do, you see I would add up everything in A1, A2, and A3. So I have cardinality of A1 plus cardinality of A2 plus cardinality of A3. And just like when we had only 2 sets, now what's happened is I've added A1, added A2, added A3. So everything, for instance, in here was counted both by A1 and A2, right? And similarly, everything in the intersection of, this was counted A1 and A3. I misread my index. Everything in the intersection of A1 and A2 was counted twice. So everything here in this red has been counted with A1 and with A2. And finally, everything here was counted with A2 and with A3. Okay, so we need to subtract, just like we did with 2 sets. So we subtract the number of things in this intersection minus the number of things in this intersection minus the number of things in, A2 intersect A3, like this. So far, what have I done? Well, here, here, and here, I subtract, subtract, subtract. Now, what's the problem? Okay. What happened? Everything so far, if you are in this that's just blue, we added it 1, 2 times, we subtracted it 1. So now it's been counted the number of times it's there, which is 1 time. Everything in just this green, we added it 1, 2 times, subtracted it 1, we're good. Everything in just this red, we counted it 1, 2 times, subtracted it 1, we're good. But this is not the end of the formula, because notice here in the intersection of all 3, what's happened here in this region? Well, let's go back to the beginning. Everything that's in A1 and A2 and A3, we counted it for A1, 1 time, for A2, 2 times, for A3, 3 times. Then we subtracted off for A1 intersect A2, subtracted off for A1 intersect A3, subtracted off, so it's in each intersection. It was added 1, 2, 3 times, subtracted 1, 2, 3 times. So now we haven't counted this at all. We must add it back. We add in A1 intersect A2 intersect A3, this cardinality. And this is inclusion, exclusion for 3 sets here. Now, as you can imagine, it gets more complicated when you go to 4 sets, 5 sets, 100 sets. You keep adding, subtracting, as I mentioned. Include, exclude, like this. I don't want to get to that level of abstractness just yet, okay, because it will be fun when we do. But first, I want to use this. Now, how am I going to use inclusion, exclusion for 3 sets? I mentioned a big goal, we are doing this, is to count onto functions. So let's suppose the cardinality of A is n, and the cardinality of B is 3. And, well, we know in order to, if n is less than 3, we have no onto functions, right? So if n is 0 or 1 or 2, there's no onto functions. So let's suppose here that n is bigger than or equal to 3. Okay? Now, we will count onto functions f from A to B. And how am I going to do this? Well, guess what? Inclusion, exclusion. But it's a little bit sneaky. I think it's a little bit fun, but it looks a little bit abstract at first. So just hold on for a second. I'm going to define some sets, and it may not be obvious how I'm going to use them until I erase and come back up here. So let me define. I'm going to define 3 sets, C1, C2, and C3. And you see we have this stated for 3 sets, so I will be using this formula with C1, C2, C3. Okay? Well, C1 is going to be all functions such that, oh, well, before I do this, let me just give some names to the elements in B, excuse me. So let's suppose B equals B1, B2, B3. And now I can define my sets. This is all functions such that B1 is not in the image of F. And this one is all functions such that B2 is not in the image of F. And finally, this one, maybe you can guess already, this is all functions such that B3 is not in the image of F. Now, you might be wondering, what are you doing with these? I thought you wanted onto functions, and none of the functions in C1, C2, C3 are onto. This is why I said just hold on for a minute, because I will get there. So let me erase all of this up here, and I'm going to draw a picture, and we will figure out where the onto functions are in all of this. Okay, maybe before I draw a picture, let me have one more thing that I put down below because I do have space. I need a universe. So my universe U is going to be all functions. This is all functions. And also one thing we know how to count this. Well, I'm running out of space. Maybe I'll do it above. U is the one thing we know how to count right now, right? Well, and some of these, as we will discuss. We don't know yet the number of onto functions from A to B. That's what will come out of this calculation. Okay, so let's draw a picture here. We have our universe U. This is all functions from A to B. Then we have C1. This is an abstract picture, okay? We will see, it doesn't actually look like this, but we'll see in a minute. It's just an abstract Venn diagram at the moment. This is C1, this is C2, and this is C3, okay? Now, we have to make some observations. This is all functions. Notice here, this C1 union, C2 union, C3. What is this set? Well, this says that either B1 is not in the image, B2 is not in the image, or B3 is not in the image. So this contains all functions f from A to B such that the image of f is not equal to B. We always know subset in this direction, okay? And if these are not equal, it means there's something in B that's not in the image, right? And that means either B1 is not in the image, or B2 is not in the image, or B3 is not in the image. So this is what's in this union. Therefore, if we want the set of onto functions, so the set of all f from A to B, such that f is onto, this is equal to you take the universe and subtract off this. Okay? Now this is how we're going to count it, because we can count the number of things in U. I started 2 down here and then I waited. And we can count this using inclusion, exclusion. Together we will get the number of onto functions. Okay, this is fabulous. So now let us count the number of things in U, and maybe I will even go down here to do my little side work. Here, right? What is a function from A to B? Well, if A, again, maybe I'll put this here, A is A1, A2, A3 to AN, what I need to do is specify f of A1, okay? Specify, this we have discussed, but it's important enough in this argument to discuss it yet again. I specify f of A1, f of A2, f of A3, and so forth, f of AN. Then I have a function. And B has 3 things, so I have 3, 3, I have 3, 3, 3, 3 possibilities. Each element goes to either B1, B2, or B3. So I have 3 for each. We have a total of 3 to the n. Okay? So the number of onto functions this is going to equal, well, we have 3 to the n minus, I'll write it this way, C1 union C2 union C3. And then I need to inclusion, exclusion on these. Well, this is when I wish I had a bigger board. We will make do, especially for inclusion, exclusion. It's probably the time I wish I've had it the most so far. But let's think about this. This I can erase, we understand. Okay. Maybe I'll erase my Venn diagram, sadly, because I love it. Okay, draw a box. Now let's count. Let's think about the cardinality of C1. Well, this is all functions, but B1 is not in the image. So what happens here? Oh, sorry about that, that hurt. Let me make sure it's still in focus. Okay, good. Here, we no longer have 3 things to choose from, 3 things to choose from, etc. We can only have 2 things. Either f of A1 is B2 or B3, B2 or B3, B2 or B3, like this. So the number of things in C1 is 2 to the n. And generally, that's true for any of these, right? Same thing for C2, same thing for C3. We get 2 to the n because if, for instance, if B3 is not in the image, then you either put B1 or B2 in each one of these. You have 2 options for each value can go to one of 2 things. Certainly can't go to both. That wouldn't be a function. Okay, well, so far, so good. We have a minus. There's 3 of these. So we have 3 times 2 to the n. That's for the individuals, right? Then I have to subtract off the sum of things like this. I'll go back to blue for my side work. In inclusion and exclusion, we have things like C1 intersects C2. We have C1 intersects C3 and C2 intersects C3. This would be the next term, right? I add up these, okay? Then I subtract these, and then at the very end, I add back the intersection of all 3. Well, here, C1 intersects C2. This says B1 and B2 are both not in the image. Well, there's only one function like this. It's where every single thing here, you only have one option, here, here, here. Now I'm working with this case. Maybe I shouldn't have it down here because it looks like I'm still counting all functions. But it says you just map everything in A to B3, and you don't have any other choice. Similarly, there's one here. This one says you map every element of A to B2, and this one says in this set, there's only one function, is where you map everything in A to B1. Okay, so each of these are 3. Uh-oh, wrong color. The last thing I was going to, or the last part of this, of inclusion exclusion, would be counting. Okay, I will still leave my set C1, C2, and C3 up because we're using those. The last part is, right, we have all singles. Then we subtract all intersections of 2. Then we add back this. Well, zero, right? Because what this says is you have a function from A to B, but B1, B2, and B3, they're all not in the image. Well, there's no functions like that, right? There's no functions. I'm trying to even think what that would say about the second coordinates. It just doesn't happen, right? B has 3 things. There is no function that avoids all 3 of them in the image. That just does not happen. This cardinality is 0. So this, when we add back in, this is why I'll put a parentheses, and then I'm going to erase some more, and I'll go back and talk about my Venn diagram. But this is why I said that my Venn diagram, which was here, was not exactly accurate because I drew it as sort of a generic Venn diagram. And now that I have a little more board space, let me do again. It looks something like this. A1, A2, uh-oh, it's C1s. Sorry about that. C1, C2, and C3, and here was our universe U. But now we know it's not accurate. It doesn't look like this because in here, this is empty. So they don't really intersect like this. And maybe this is when you realize, I'm going to erase, okay, this is not an accurate picture. So maybe we have C1, C2, and then something down here, C3. The picture is more accurate, something like this, where now you see that any 2 sets intersect, but all 3 do not, right? It's probably not, you could probably do a better Venn diagram, but it's an illustration, okay? That is more like this picture rather than the one I had drawn. Okay, well, now let us just distribute the minus sign. We have 3 to the n minus 3 times 2 to the n plus 3. So this we have counted. This is the number of onto functions when the cardinality of A is n and the cardinality of B is 3. Okay? Now, before I do anything else, let's just do a little sanity check, because I'm about to get a little bit more complicated, not only with inclusion, exclusion, but also with onto functions. And it would be really nice to understand what we have done so far before we move on. So let's just consider when n is 3. Okay, in this case, a function from A to B, they have the same cardinality. This is going to be onto if and only if it's 1 to 1. I think I have that proved in one of my function videos from last semester. So it was like an example video. But in any case, this is true. If you have two sets of the same cardinality, knowing it's onto or 1 to 1 implies the other. Okay, so we should get, because we know that this formula is just going to be the same as the number of 1 to 1 functions, we should get from this formula, well, we know the number of 1 to 1 functions. You have 3 choices for f of a1, 2 choices for f of a2, 1 choice for f of a3. This is 6. So we should get 6 from this formula. This is what I mentioned. It's a sanity check. Make sure that we both have the right formula and put it into light of something that is understandable. So here we would get, let's check, we get 3 cubed minus 3 times 2 squared plus 3. This should be 6. This is 27 minus, oh, I was about thinking that I didn't have it right. N is 3. Okay, now I have a better chance of getting it right. I knew it didn't look right at the beginning. 27 minus, okay, now it looks better. 3 times 8 is 24, and then plus 3. And you see here we do in fact get 6. Okay, so this makes sense in terms of something that we know. When A and B are both 3, we do get the same number as if you just counted the 1 to 1 functions. Okay. Now, let's discuss general inclusion, exclusion. And we will discuss the formula for general onto functions whenever the cardinality of A is bigger than or equal to the cardinality of B. Okay. If we have the general, let's mention it now, inclusion, exclusion principle, and then we will use it. Well, this says something about the cardinality of a union of, let's say, I'll say it in terms of A1, A2, A3 out to maybe N, if these are finite sets. Okay? Then the number of things in the union okay, well, my Venn diagram, if I tried, is not going to look very accurate, but we can think. First of all, we add up all of the individual ones. So this is all overall I. I goes from 1 to n. Maybe I will write this, although I won't be writing it on all of them. We have n of them. Oh, I know what I'll do. It'll make it match the other ones. This is all for all I. And then there are, well, there's n choose 1, which is n terms here. And this will match when we start doing some other ones. Then we subtract off the sum. I'll just say I not equal to j of these intersections. And here there are n choose 2 terms. Okay. And then we will add back the sum. Well, again, we cannot have I equal to j, also not equal to k. We need them all to be distinct indices of triples. Here we have n choose 3 terms, and this will continue. This is what I was saying. When you include, you exclude, you include, you exclude. The minus signs they shift, they alternate, I should say. First, you add up all the individual things. Then you subtract off all the intersections. You add back all the triples. Guess what? Subtract off all the 4 tuples, like this, the intersections of them, okay? At the very end, so the next one would be a minus. Oops. And then we have a dot, dot, dot. The very end. Well, we come to the intersection of all n terms. A1 intersect A2 intersect all the way out to A sub n. And we have to figure out the appropriate power of minus 1. Here we have 1 term is positive. We have 2 terms is negative. 3 terms is positive. This suggests the power is a minus 1 to the n plus 1, or n minus 1 is fine too, like this. So you have all the singles, subtract off all the intersections of pairs, add back the intersections of triples, subtract off the intersections of 4 tuples, like this. Include, exclude, until you get to the very end, and it comes with a minus 1 to the n plus 1 power. Okay, this is the general inclusion-exclusion. Now, guess what? We'll do it below. Or I can erase. I'm not sure how to start. Maybe I will erase so I can work down. But this is inclusion-exclusion, and I'm about to use it on 2 functions. This is going to be fun. I will say that, but it's going to get intricate. Okay, we'll be okay. So suppose the cardinality of A is n. Cardinality of B is m. And now, because I want to count them, I'm going to give it a name. Let's say T is the set of all f from A to B, such that f is onto. Now, we will assume that n is bigger than or equal to m, because we know, and we proved with pigeonhole principle, that if n is less than m, the answer is, or this cardinality T is the empty set. So I'm really interested in when it's not empty. Let's count the number of things in T. Well, part of the reason I started with m is 3 is because it was a little bit less intense than the general case, and hopefully this will go through a little easier having seen m is 3 already. So I will define C1 to Cm. These are all inside U, where U is all functions from A to B, and let's say Ci is all functions from A to B such that BI is not in the image of F. And again, I forgot to do it this time, but let's do it now. I'll put it in parentheses again. That B, we will just say it's B1, B2, out to BM. So we have M sets, C1 through CM, and each one says that, or the ith set says that BI not in the image. Okay, so just like when we had M was 3, we have similarly that this T, maybe I'll say notice T, as I've defined it, which is all onto functions, it's this all functions but set difference C1 union C2 union CM. For the exact same reason as before, if you are not onto, it means the image of F is not all of B. And that would say that one of these BIs, at least one, is not in the image, so you would be in one of these, right? So if you take all functions minus this, what we are left with is precisely the onto functions. And so we can count the cardinality, or the cardinality of T is the cardinality of U. Okay, also, I'll mention this now, the cardinality of U, we know. We can still think of it as a list of length n, f of a1, f of a2, f of a3, like this, where the elements this time, instead of coming from a 3-element set, they come from an m-element set. So this is m to the n. Okay. So now is when we get ready for inclusion, exclusion. I would say strap in, hold on to something. Here we go. Cardinality of T equals, well, is going to be m to the n minus the cardinality of this union and this is m to the n, oh goodness, I have a little bit of space, minus, no, maybe I'm going to go to the next line. I think this would be wiser. So this is m to the n. Here is where I'm going to start using inclusion, exclusion. We have minus, okay? We have the sum of cardinalities of the individual ones. And as I mentioned, there are m of these, m choose one of these, right? There's m in total. Okay, then I subtract the sum overall, ci intersect Cj. Again, I is not equal to j. And I mentioned there were m choose 2 of these. Then I add the sum of all ci intersect Cj intersect Ck, where I, j, k, they're all different indices. There are m choose 3 of these. We would then subtract off the intersection of all 4s, add back the intersection of all 5s, etc. But I will just go to the end. It's going to be a minus 1 to the m plus 1, and then we have the intersection of all of them. Intersection C, the last one is a m, like this, parentheses. Well, now comes the counting. But you see, based on what we thought about already, it's really not bad. I would say this looks more overwhelming than it is because there's a lot of indices and a lot of sums. Okay, so here we go. Let's start counting. M to the n minus big parentheses. Okay, we're going to go one by one and think about these. First of all, this is the just single sets, just the number of things in each one. And first of all, for each of these, how many terms are in the sum? And then we count. Okay, How many terms are in the sum? There are m, choose one, terms in the sum. And then maybe I will think about some stuff below, which I might erase. This will be my little side work. So any of these, the cardinality of CI, okay, this is very much like we already thought about, where you have this string or list of length n, f of a2, f of a1, right? But in this set, you can put, this can be anything in B except BI. So you have m minus 1 possibilities for f of a1. You have m minus 1 possibilities for f of a2. This continues m minus 1 possibilities here. Okay, before, when this was only 3, remember, we had, well, there were 2, like this. But general m, you have m minus 1 to the n. Okay, so this is this quantity because every single one of these terms is the same number, m minus 1 to the n, and there are m choose 1 many terms. Okay, this argument will be similar for each, well, until we get to the end. Now, then there's a minus. Now again, and I mentioned this when we first wrote the general inclusion exclusion, how many things are in this sum? Well, there are m choose 2. M choose 2 in the sum. And then down here I will think. This is my thinking. I'll leave it up until I need to erase it. If I count this, CI intersect CJ, of course I is not equal to J, f of a1, f of a2, etc. to f of a(n), well, B1, or excuse me, BI and BJ are both not in the image. And so I have m minus 2 left in here. M minus 2, m minus 2, out 2, m minus 2. This cardinality you can see, right? And it's the same anytime I is not equal to j, because it's the same number. You just can't map to bi, and you can't map to bj. So you have m minus 2 elements of b you can't map to. It's this. So each one of these has cardinality m minus 2 to the n. This is starting to look really pretty. What would you imagine here? Should I do this one? We'll do it. It's going to be a plus. How many terms are here? Well, if these are all distinct, and that's what I mean when I write that I, j, and k are all distinct indices, we have m, choose 3. And then, if you think down here, how many are in any one of these? Okay. Well, the only thing that changes, if you want to look at the cardinality of CI intersect CJ intersect CK, where I, J, and K are different indices, is you have, now there's 3 things from B that you can't map to. So you have m minus 3 choices. M minus 3 all the way out to m minus 3. This is why I asked, do we want to do this one? Because you see, the pattern is exactly what we've seen. And this pattern will continue exactly like this, where we have m choose k, m minus 3 to the k, except this is when we really have to think some, okay? Let's think about the very last term here. Uh-oh. this one. And then we will finish the sum. We'll put up dot, dot, dots and put whatever comes at the end. You see this one, just like when we had only 3 sets. This one says B1, B2, well, all the way out to BM. So every single element of B is not in the image. Well, if you're mapping from A to B and no elements of B are in the image, there's no functions like this. So this cardinality here is 0. Just like we saw when B was 3, the intersection of all 3, C1, C2, C3 was 0. But we can't just leave this as a dot, 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 because it would look like it goes forever, and it certainly does not. So that means that the last non-zero term will be when you have, let me erase and I'll start talking about it, because this we understand. Let's look at the last non-zero term, maybe in green, the last non-zero term. Well, what's it going to look like? It will look something like this. I'll just write out one of them because I don't have to do so many I's and J's. We will have an M, choose M minus 1. Oh, there's a minus 1 to the power. Okay. Instead of an M plus 1, it's going to be a minus 1 to the M. It's the term right before, okay? Then we will have this many terms, okay? Running out of space. That's okay. In the last non-zero term, well, the cardinalities look like this. They look like this. C1 intersects C2, intersects C3, out to, there's an intersect, CM minus 1. It's not only this one, it's all possible intersections where only one of the sets is not there. Okay, so for instance, you have C2 to CM, C1 to CM minus 1, and you have a total of M in total, which is this quantity here. Well, let's just count this one because they all have the same cardinality as we have seen in the other terms. What does this say? This is all functions from A to B, such that B1, B2, B3, B4, all the way out to Bm minus 1, not in the image. There's only one thing here, and it's you have this Bmth thing, and you have all these other ones not in the image. It maps every single element of A to this. Okay? I got to put one more so that, well, okay, I could keep adding. I just needed to make it to where we have more things in A than we do in B. All right, that's what we're counting here. But you map everything to Bm. That's the only possible function here. So this cardinality is 1, and similarly, any of the ones where you have M minus 1 of the different sets intersected, they just all map to whichever element is not included as a set here, right? If that makes sense. So it maps to Bi if Ci is not in this. So all of these have cardinality 1. This is the last one. Now, then there's a parentheses, which I will also close in blue because I opened it in blue on this side. Well, this is the number of onto functions. Let me erase this comment or our counting argument about the last non-zero term, and I will make one more step, and then that will be about the end. So I can continue here. And there's a pattern, right? M choose 1, M choose 2, M choose 3, etc. This one, does continue the pattern. If I put an M choose 0 in front of here, nothing has changed because M choose 0 is 1 and the coefficient in front of here was 1 to begin with. Then, of course, I have to distribute the minus sign. So let's write this as one big sum. So this is equal to, so K will go from 0 to M minus 1. And then, okay, wonderful. What do you notice? Well, we have a minus 1 to some power, which we will do at the end because I also have to think about distributing. Then we have M choose K. We have M minus K to the n. And now I'm ready for my power. When K is 0, it should be positive. When K is 1, it should be negative. Don't forget to distribute. When K is 2, it should be positive. When K is 3, it should be negative. Well, okay, this is just a minus 1 to the K, like this. So, all of this work, inclusion, exclusion, which was a lot of fun. We all get to hear.